So our next and final factoring method is going to rely on a formula that we actually saw back in chapter 5. It was a formula that we mentioned we didn't need to use, as we could just straight distribute terms of polynomials to multiply them. However, we looked at a specific situation here. The name for this formula was the product of the sum and difference of two terms. It's a very specific situation. It's not just any two binomials, but it's two binomials where the first terms are the exact same, the last terms are the exact same, and there's one plus and one minus between the two terms. We saw that if you were to distribute all this out, our two middle terms were the same, but one was a positive, one was a negative, so they would cancel, leaving us with just the a squared minus the b squared. So this was a formula we saw in chapter 5, but again, I didn't really emphasize it, just mentioned it was there if you wanted to learn it and use it. However, it gives us insight into knowing that now, as we look at factoring, for the reverse of multiplication, if we see a polynomial that fits this exact pattern, this exact form, we know that it could have come from this original product, this original multiplication problem. And the issue is, in this form, only two terms, we aren't able to apply our other methods. GCF won't do it, grouping definitely won't do it, and the number game isn't going to necessarily help us. So with two terms, with a binomial, this is a new method that we're going to want to use to, again, just see if a polynomial fits this pattern, because if so, we know it will factor back into this form. So the real key is just first identifying the form. It's a binomial with a subtraction of two squares. Notice this first term will have to be the square of something. This second term will have to be the square of something. And that's really where the work boils down to. When you're trying to identify this, really just work on identifying the values of a and b. Right? If you can do that, then we can break it apart. So let's look at these first couple. So as I'm looking at this polynomial asked to factor it, remember, no matter what, first step, GCF. GCF is a 1 here, doesn't help. So now, you're looking at this, and it's two terms. So again, none of our other approaches can help us, and what we're looking at, what we're going to ask the question is, does this fit that pattern? Well, first of all, it's a minus. That's good. There's the difference. So the question is of squares. So what I do, about the only real work that I show on these problems is off to the side, I ask the question, can we identify the a and the b? Meaning, can you figure out what it would be that you would square to get this term x squared? So the question is, what squared is x squared? Well, you basically say it when you say it. X squared would give me x squared. And same with b. What would you square to get a 9? Well, that just comes from knowing your perfect squares. 3 is the number we square to get 9. And we've found the a and the b that fit this exact pattern. So then we just need to have memorized the formula of a plus b, a minus b, and use that a and b plugged directly in. X plus 3, x minus 3, and we're factored. So that's it. Identify the pattern, identify the a and the b, plug them into the known formula, and it's factored. And again, as always, you can multiply this back out to check to make sure it does get back to where we started. So don't forget that. Number 2. First step, GCF. GCF is 1. And so now, it's two terms. So again, the question, this is the last time I'll probably write this out, but right there we're looking, does it fit this pattern? First and foremost, it's a minus, so that's good. Now, the question's of squares here. What would a be? What would you have to square to get 4x squared? Well, 4 would come from squaring 2, and similar to the last problem, x squared would come from squaring x. 25 would come from squaring 5, and so, again, our formula, a plus b, a minus b, with that a and b, 2x plus 5 times 2x minus 5. All right, so do several more here. All right, first step, GCF. notice we've got a GCF here of 8 and 50. The GCF would be a 2. So let's factor that out first. 2 factors out. 4x to the 6th minus 25. Now notice what we're left with is a binomial. So as we've been seeing, don't just stop at a GCF. The GCF may allow us to do more with the problem. And in this case, I will still write the a and the b off to the side. I'm just not going to write the formula underneath every time. But it's the same question. If this works, if this breaks down further using our difference of squares, then we should be able to answer the question, what would you square to get 4x to the 6th? Well, again, to get a 4, you square a 2. Now, x to the 6th, you got to ask, what power of x would you square to get x to the 6th? You're saying we've got x to a power and then squared, and we want that to be x to the 6th. Well, remember our exponent rule. Whatever this power is and this power, that's the power rule, and we multiply those two numbers. Those two numbers multiply to give us a 6. That means that right there would have to be x to the 3rd, because x to the 3rd squared would be 3 times 2 would give us that 6. Essentially, any even exponent can be gotten by squaring whatever half of that number is, right? Half of 6 is 3. X to the 3rd squared would be x to the 6th. And 25, we know it comes from 5. So we've got the 2 sitting out front, and then our a and our b. 2x cubed plus 5 times 2x cubed minus 5. I've also mentioned it does not matter if you put the plus or the minus first here, whether you put a minus and then a plus or a plus and a minus. This is just the way I've always learned the formula, so that's the order I'm going to go in. All right, number 4. First step, GCF. Oh, before we go any further, I want to go back real quickly and point out, if we had not found this GCF of 2, we would have had an 8 and a 50. Neither of those numbers are perfect squares. You would not have been able to break this down at all with anything until we did this first step GCF that allowed us to see that we could have an a and a b. So this is an example of where if you do not get used to that first step GCF, you cannot do anything to this problem. Absolutely unable to until the GCF comes out, and then, in this case, it breaks down further. So keep that in mind. Always first step GCF, even though a lot of times it's going to be a 1. All right, so we're going to try the difference. I see a minus sign, difference of squares. What do I square to get 16x to the 4th? Well, 4 squared is 16, and using that same trick, it's x to the 4th. Half of 4 is 2, so that'll be what we would square. And 1 can always be gotten by squaring 1, so that works. And we've got our a and our b. So we'll break this down to 4x squared plus 1 times 4x squared minus 1. And now before I put a box around that, this kind of ties into the next section too, where we'll pull all of our factoring techniques together, but we always want to make sure we're factored completely, as the directions say. That means breaking down anything that can be broken down. And in this case, if we look at what's left, now this is close to something we might want to break down, but notice this is not a difference of squares because that's a plus sign. You can ignore it immediately once you see that as far as the difference of squares. But look at this other binomial. It's 2 terms, separated by subtraction, 4x squared, and 1, we can absolutely find an a and a b for that. For this and this. For a, to get 4x squared, you'd square 2x. And again, 1 can be found by squaring 1. So we can break this part down further, but not this part. This has to stay 4x squared plus 1 because we don't have a formula for the sum, the addition of squares. This only works for the difference, the subtraction. But now I can break it apart to 2x plus 1 and 2x minus 1. Now at that point, we're done. We can't break down further. That's not a square. This is not a difference of squares. But like I said, in this section and going forward, it'll kind of be this idea that since we have this difference of squares approach to factoring, just because we break it down into binomials doesn't mean we're done. We're going to look at those binomials and see if this technique can break them down further. All right, next one. First step, GCF. Okay, looks like we've got a 4 that can go into both of these. So let's pull that 4 out be left with 9m squared minus 25n squared. I'm going to go ahead and point out real quickly here. 36 and 100 are squares, and you might have been tempted to jump right into the difference of squares. If you do that, you will very likely miss that there's a GCF, and you will not have the fully factored answer in the end. We'll talk about that again here when we get to the final answer. Just want to point that out. Always look GCF first. Now that we've done that, the question of A and B for this problem, what do you square to get 9m squared? 3m. What do you square to get 25n squared? 5n. And so 4 times 3m plus 5n and 3m minus 5n. And then that is finished. Notice, if you would have tried to break this down immediately with A and B, you would have had a 6m and a 10n, as in things that square to get 36 and 100. But 6m plus 10n and 6m minus 5 or 10n would not be a fully factored form. So that's why it's much safer and better always to look GCF first. All right, number 6. Speaking of, first up, GCF, and there it's a 1. Now here, we notice we could find an A and a B, but that's not a minus sign. So we do not break that down further, just like the one we mentioned above, same kind of scenario. And in this case, just a reminder, when you get to a polynomial where there's absolutely nothing, not even a GCF, that you can do to break it down, we refer to that as prime. And number 7 down here, last one, first step, GCF is a 1. And make sure you're not trying to force this difference of squares, because I do see a minus sign, and I think of that as an A, but B, again, what would you square to get a 6, right? You could even say A is X, but when you look at for B, 6 is not a perfect square, right? We don't know what you would square to get that. Don't think half of it, right? Half of it doesn't work. Or if you do think half of it and you try 3's, just check your answer and you'll realize it doesn't work. So this is another example where GCF didn't help us and nothing else is going to factor this, so we will call that prime.